Okay, so the third change that can happen in a system is changes in pressure. Changes in pressure only affect equilibrium systems that have gaseous products and or reactants. So if there's no gas present in the reaction, changes in pressure are not going to affect the equilibrium system. When you increase the pressure of a gaseous system, it will cause the equilibrium to shift to the side with fewer gas particles. When you decrease the pressure of a gaseous system, it will cause the equilibrium to shift to the side with more gas particles. If the system has the same number of moles of gas on each side, changes in pressure do not affect the equilibrium. Adding an inert gas, so this is basically adding a gas that is not part of the system or part of the reaction. It also does not affect the equilibrium, since the partial pressures of the gases in the reaction are not affected. And then changing pressure does not affect the value of the equilibrium constant. So in the last video, we talked about temperature changing the equilibrium constant. That is the only one of the four changes that will affect the value for the equilibrium constant. So we have some examples here. The first example, we have P4 solid reacting with 6 chlorine gas particles, producing 4 PCl3, which is a liquid. So the first change that happens is that you're going to increase the container volume. So when you increase the container volume, that is going to cause your pressure to decrease. So that's kind of something that's important. Even though we're not given a specific change in the pressure, by changing the volume, we are going to change the pressure. So if we are decreasing the pressure, it's going to shift to the side with more gaseous particles. Well, chlorine is our only gaseous particle, so that's going to cause this equilibrium to shift to the left. When you decrease the container volume, that is going to increase your pressure. And then when you increase your pressure, it's going to shift to the side with fewer gas molecules. Well, you can't get any fewer than none, so it's going to shift to the right. And then adding argon gas. We don't see argon anywhere in this reaction, so this is that inert gas. This is going to have no effect or no change on the equilibrium. The second example says PCl3 gas reacts with chlorine gas and produces PCl5 gas. The first change that we see is a decrease in the container volume. Well, decrease in container volume increases the pressure. So now when we increase the pressure, we want to shift to the side with fewer gas particles. Well, we only have 1 mole of each thing in our reactant, so we have 2 particles of gas, 2 moles of gas in the reactants, and 1 in the products. So if we are shifting it to the side with fewer gas particles, we're going to shift it to the right. And then adding helium gas. Again, that's not a part of our equation. That is an inert gas. That is going to have no change. So we have 2 molecules and then we just have 1 molecule here. And then our last example, we have PCl3 gas reacts with 3 NH3 gas, producing P NH2 3 gas and 3 HCl. So the change that we're making here is we are increasing the container volume. So as we've talked about, increasing the volume is going to decrease the pressure. So now we need to look at decreasing the pressure shifts to the side with more gaseous molecules. So we have 1 mole of PCl3, 3 moles of NH3. So that's a total of 4 in the reactants. And then we have 1 mole of PNH2, and 3 moles of NH4. Well, we have 4 in the products. So the other thing is if the system has the same number of moles on both sides, then it has no effect on, or no change on, the equilibrium. So even though the pressure is changing, it's not going to drive it either way for the equilibrium. So the production of ammonia from nitrogen and hydrogen, raising the temperature favors the reverse reaction, which absorbs heat. Temperature and pressure are carefully produced in the industrial production of ammonia, which exploits LeChatelier's principle to maximize the amount of product obtained. The production of ammonia is of tremendous importance in feeding the world, since ammonia is used in fertilizer. So here you can see it's a Haber's process, and when you start with nitrogen and hydrogen in the compressor, and then it's unreacted, catalyst is added, and then it moves into NH3 storage. In the production of ammonia from nitrogen and hydrogen, raising the pressure favors the forward reaction because there's 4 moles in the reactant, 1 mole of nitrogen, 3 moles of hydrogen, and in the products there is only 2 moles of gas. So that's shifting in the direction with fewer gas molecules. So I just wanted to show you those examples since ammonia is such an important part of lots of things that are needed for daily life. Just how these changes can help with that production. And then the fourth change to a system is the addition of a catalyst. So we talked about a catalyst in chapter 12, and we said that adding a catalyst just speeds up the reaction. It provides a pathway where less energy is required to make those products. However, adding a catalyst does not affect equilibrium, so it has no change on the equilibrium. In this example, we're considering the reaction of 2 moles of nitrogen dioxide decomposing to form nitrogen and oxygen, which is an exothermic process. So we want to look at these changes and predict what is going to happen to the concentration of oxygen, but also what's going to happen to the value of K, and which direction is our reaction going to progress. So when nitrogen dioxide is added, we're increasing the concentration of our reactant. That is going to drive our reaction to the right. And then when we think about the concentration of oxygen, we are going to increase it because we're forming more products. Concentration has no effect on the K value, so it will stay the same. When N2 is removed, that's one of our products, we're going to shift our reaction to the right to replace that. And this is also going to cause the oxygen concentration to increase, and the K value stays the same. When the volume is halved, this is going to increase the pressure. And so now we need to look at our number of gas molecules. So we have 2 molecules in the reactants and 3 in the products. So this is going to shift it to the side with fewer gas particles. So we're going to shift it to the left. This is going to cause the oxygen concentration to decrease, and the K value is also, oh, I'm sorry, I got off the line. The K value stays the same on this one. I apologize. It's like pressure does not change the K value. Why am I writing that? Sorry. Okay, and then in D, helium is added. That's our inert gas, so that is no change. When the temperature is increased, that is going to shift. Since this is an exothermic reaction, it's going to shift it to the left. And it's going to cause, since we're going to shifting it to the left, the oxygen concentration is going to decrease. And the K value is going to decrease. There's my K decreasing. And then a catalyst is added. That is going to have no change on the equilibrium systems. So that is it for LeChatelier's principle. Thanks. Have a great day.